Okie dokie. So, now we're going to talk about, this is leading into phi factors, the strength reduction factors. Up until this point, we've been dealing with a lot of single layers of reinforcement. Single meaning those don't exist, right? This is a double layer of reinforcement. And we've been talking about when the steel yields, the yielding of the steel. And if it's all in one line, it'll all yield at the exact same time. But if we look at the strain profile of this section, right? Like that. If I look at the strain profile, if this is layer 1 and this is layer 2, the strain in the steel of layer 2 is different than the strain in the steel of layer 1. So I want to know when will any reinforcement start yielding? Not necessarily all of it, but any. Obviously, you can probably tell from this from that triangle there that the value of the strain in the steel in the bottom layer, layer 2, is going to always be greater than the strain in the yield and the steel of the top layer because of this triangle, right? ES2 will always be greater than ES1. So previously I had defined this value D, which is the distance from the extreme compression fiber to the centroid of my reinforcing steel. And this is 2 layers, so the centroid would happen right in the middle. Or 2 equal layers, right? The centroid would happen right in the middle, D. That's the effective depth. Extreme compression fibers up at the top to the centroid of your longitudinal tensile reinforcement. And I like to use my similar triangles to find strains, right? So now I want to find a new dimension known as dt. And now those things are going different ways. dt is the distance from my extreme, I don't need that, from the extreme compression fibers to the extreme layer of reinforcement, of longitudinal tensile reinforcement. We'll write that down. To the extreme layer of longitudinal tensile reinforcement. And it's to the center of that, even though that line is not terribly great. This one goes to here, this one goes to the centroid between the layers. I want to know this dimension so that I can determine when any reinforcement starts yielding. It will obviously be the outermost reinforcement that will start, the most extreme outermost reinforcement, tension reinforcement that starts yielding before others. So if I know that dt, then I can calculate that. I'm going to use this value when any reinforcement starts yielding to calculate my phi factor. So I'm going to go to the next page. I want to know if it is tension controlled or compression controlled. So I'm going to draw two strain profiles. After a lot of experiments, they decided to define values. So if I'm talking about tension controlled, as always, I assume that my concrete strain at the extreme compression fibers is equal to ECU, which is 0.003. But for it to be tension controlled, I want the strain in my steel to be beyond yield. I want to make sure that it has yielded. So I've got EY plus, I'm going to add on 0.003. This is the tension controlled limit. Tension controlled limit, TCL, not TLC. Doggo chase the waterfalls. The neutral axis associated with this is called CTCL, right? The neutral axis depth associated with the tension controlled limit, CTCL. And should have drawn this first, but we're talking about the extreme tension fibers or tension reinforcement, so DT. If I look at a compression controlled strain profile, I still have the strain in my concrete equal to ECU. But now I'm only going to assume the strain in my steel is the yield strain. This is the compression control limit, aka CCL. And I'm going to define a neutral axis associated with this. CCL. This means what these two limits are. If the strain in my extreme tension steel is greater than the yield strain plus 0.003, then I'm definitely failing in tension. If the strain in my extreme tension steel, right, these far bars down here, is less than my equal to or less than my yield strain, it's probably like right up to that yield strain, right? then I'm in a compression controlled environment. Obviously, there's some gray area between adding nothing and adding 0.003, and that is called the transition. Where you're not sure, it could probably be tension controlled, but you're not sure. So if I go look at strength reduction factors, that's where this all comes into play. If I look at my phi factor, the strength reduction factor phi right? The strength reduction factor phi in accordance with the table, except as modified by something else. So I'm talking about moments here. It says my phi varies from 0.65 to 0.9 in accordance with 21.22. Super. So I'm going to go look at 21.22. 21.22. For deformed reinforcement, ETY shall be FY over ES. You can take ETY equal to 0.002. We'll talk about that in a second. What I'm most excited about is this, the strength reduction factor for moment, axial or combined. If my strain is less than my yield, I'm compression controlled. Otherwise, I'm tension controlled. Or if it's greater than yield plus 0.003, I'm tension controlled. If you're in the middle, you get to interpolate. This phi factor breaks it up by what kind of transverse reinforcement you have. When we're talking about transverse reinforcement, I should put a picture up here. So I'm going to have to draw one. Oops. Yeah, there it is. I was like, I'm pretty sure I have one. It's by reinforcement. So let's write down what this is, and then we'll. So, and I should have said, instead of ES, I need to correct my notes. I meant ET. That is ET. ET is defined as the strain in your extreme longitudinal tensile reinforcement. Tensile reinforcement. I go back to this thing, right, I just said ES2 is in layer 2. That's my layer 2 is my extreme tensile reinforcement, so that would be my ET. So I'm going to start with the compression control in my little chart right here. If my strain in my extreme tension reinforcement is less than or equal to the yield strain associated with that tensile reinforcement, just in case maybe you have different grades of steel. Then your compression control. If your strain is greater than or equal to your yield strain associated with that tensile reinforcement, that's why there's that T subscript, plus 0.003. And your tension controlled. If you're in the middle, then you're in transition. As I said, this is based on your type of reinforcement, transverse reinforcement. What we mean by transverse reinforcement is, actually I'm going to go to the next slide. All right, here's two different if you're looking along a beam, you're going to have your longitudinal reinforcement and your transverse reinforcement. Looks something like that, right? This is used for a couple of reasons we'll get into later. Transverse reinforcement is for shear and for also adding some compression to your concrete. There's two different types. There is spiral, transverse reinforcement. Where obviously, like if you have a circular cross section, just gonna spiral it up. There's probably some longitudinal stuff in there. And then there's everything else, which they call other. Probably because it could be, in this case, this is a stirrup, or no, this isn't a stirrup. So, yeah, stirrup or a tie, which might just be like one little dude and one little dude. They're not connected to the top. There's probably should be something up here. There can be all kinds of other things, but it's going to be like discrete little pieces of steel, whereas the spiral is continuous. So it's going to break it up by type, spiral, or other. Stirrup is often other. So tension controlled, compression controlled. Which one do you think is going to have the higher phi factor? Remember, your phi is used to reduce your moment capacity. Your nominal capacity, you're going to reduce it by a phi factor. Which one's going to have the higher phi factor? If you just yelled out tension controlled, you're right. Your phi factor is 0.9 for both types. Reinforcement, transverse reinforcement. Why, and then on the opposite end, compression controlled, spiral is 0.75 and other is 0.65. The reason for the difference in tension versus compression is compression is going to be a more brittle failure, might have a lot more unknowns with it, so you want to have a higher reduction factor. The tension controlled steel is a lot easier of a material to control how it's made. So if you're controlled by the strength of your steel, then you can reduce by less. Or your phi factor is going to be less. And then the difference between a spiral and transverse is due to the confinement that spiral reinforcement provides of the concrete. And then in transition, we literally are going to do, what am I trying to call it? Interpolation, right? 0.75. Same with our beta 1 factor, right? 0.75 plus 0.15 times ET minus ETY divided by 0.003. Alright, that's that addition that you add on. 0.65 plus 0.25, right? 0.15 is the difference from 0.75 to 0.9. 0.25 is the difference from 0.65 to 0.9. ETY over that 0.003. this table is in your ACI 318. It's table 21.2.2 on page 393. There's the same friggin' thing. If you look at it graphically, it looks like that, right? Looks like that. Now the other thing that your code said is that strain, that yield strain associated with your tension steel shall be your yield stress divided by your elastic modulus. And if it's grade 60, which is what most things are, use 0.002. Even though it's actually 0.00207, you could just round it to 0.002 for this specific calculation. Right. According to ACI, that's a 3, ACI 318, 21.2.2, no, 0.1. For grade 60, ETY is approximately 0.002. So if I put that into these two equations, ETY, EY, I'm using them interchangeably, 0.002 plus 0.003. So if your yield strain is greater than 0.005, your tension controlled, if your strain and your extreme tension reinforcement is greater than 0.005, then you're tension controlled. If it's less than 0.002, you're compression controlled. If you're in the middle, you're in transition. And we use that to determine our phi factors. So based on that, let's go back to some of those examples that we've done and determine what would have been the phi factor here. Now in this case, so let's see, in this case, single layer, right? Therefore, our D, our distance from our extreme tension from our extreme compression fiber to the centroid, our distance dt, which is the distance from the extreme compression fiber to the extreme tension reinforcement, is equal to the distance from our extreme compression fiber to our centroid of our steel, because it's a single layer, right? Therefore, the strain in our extreme tension steel is equal to the strain in that layer of steel. Since it's a single layer, dt is equal to d, and et is equal to es. We figured out ES, so ET is equal to ES, which is equal to 0.0066. So my phi factor ET of 0.0066 is greater than the yield strain plus 0.003, which is equal to, this is a grade 60. And I said that if it's grade 60, I can just use .005. So because my ET is greater than my ETY plus 0.003, which is 0.005, I'm definitely tension controlled. Maybe I shouldn't have declared victory so earlier. And my phi factor is equal to 0.9. Right? That was based off of this. If my strain in my FAR reinforcement is greater than the yield strain plus 0.003, which for grade 60, that value is 0.005, I'm tension controlled, and my phi factor, this is stirrup, but it doesn't actually matter, is 0.9. So, from my previous example, I could use a phi of 0.9. That's based off the fact that I have a single layer of reinforcement, so I don't have to do any new calculations. Now, if I had multiple layers of reinforcement, this dt equals d would not be true, and I would have to use similar triangles like I did here to find the strain in my extreme tension steel. So phi 0.9, I determine my nominal. Now if I determine my design, 0.9 times 240 kip feet you would do fee factors. Thanks.